Hey everyone, this video is an introduction to Abaqus and should help with getting an idea of how to build a simple model from start to finish. And it'll be particularly useful for the first Abaqus assignment and also useful for the following ones too. But at that point, you'll have a better idea of how to use Abaqus. So let's get Abaqus open. It's called Abaqus CAE in the, that's what the program is called. And the first thing that we're greeted with is we have to choose, to start a session, we have to choose what kind of model database we want. And so typically for all solid mechanics problems, we're always going to be using standard or standard/explicit models. You might be tasked sometime in the future to do electromagnetic models, but not in this course in any case. So let's go with that. And so on the left-hand side, we have the model tree and the model database, which is made up with a bunch of modules. For example, we have the parts module, the materials, sections, assembly, and so on. And so to build your model, you need to input all the information in this model tree, all the information that is relevant to your model. You'll note that there are many other buttons on the screen. So, well, before I get to that, I'm just going to clean this up a bit, just make it gets a little messy, and it can get messy sometimes. Right, so there are a lot of buttons all over the screen. There are buttons over here. There's these drop downs over here, all these buttons that I was rearranging just a second ago, and then all these tabs with a bunch of options. And so this can be pretty overwhelming. But truth be told, a lot of it is just built-in redundancy within Abaqus. What I mean by that is that for a given to do a certain thing, for example, if we want to create a material, there are many ways to do the exact same thing. So one option is just to double click over here, double click and start creating your material over here. You could also do that by right clicking and selecting create. Or you'll notice that when I click on these modules, these menus or these buttons change. This is because you'll notice that we're changing the module part here. And then if we go to property, then we'll have different buttons here. And so this is another, again, this is the same when I click material over here. Here I can create a material from this section, doing the exact same thing. And the same can be done as well from the top tab, excuse me, where we go material, create. There is no difference between all these buttons. It's just built-in redundancy by Abaqus. And so you can choose the way that you like to do things. I personally tend to stick by the model tree, and then sometimes using some of the tools that are available over here in the modules, but it's up to you how you want to do it. And the way that I do it in this tutorial is not necessarily the best way, again. So before we jump in, I'm going to do a few things we should always be doing to start a model. First, it's important to set a working directory. This, of course, is where all your files are going to be saved and where any simulation files will appear when you create them. When you run a simulation, you'll get new files that are generated by Abaqus. So let's go ahead and do that. To do that, we click on File in the top left, and then we head over down here to Set Work Directory. By default, it might just be a temporary folder on the C drive, but I'm going to switch it to a different folder of mine. Let's do this. Let's put into, yeah, right here. I think that's where I wanted it. Click OK. And so now any files that we're going to be creating with the model and with any simulations are going to be saved to that directory. And so let's actually go ahead and just save our model. Let's call this tutorial model. Sure. And it'll create a .cae file. .cae is for the model, is the file suffix for all model databases. So that's great. And the next thing that we can think to do is changing the name of our model. Now this isn't crucial, but it's always I think it's always a good idea to rename our models, because when we leave our model and then come back to it a week later, we might not know what exactly this is. So it's never a bad idea to give names or descriptions to what we're doing. So let's just do, I'm going to be creating a cantilever beam. Sure, cantilever beam model, doesn't matter. I'll just call it that way. Yeah, and it's also good to differentiate if you have multiple models in the same database. You can see that I can copy the model, or I can create another model. I'll just create another one for the sake of it, and I have a whole duplicate, or not duplicate, but another model tree that appears here, where I can have a whole separate model that I can run separate simulations on that's totally independent, but in the same database. But so I'll just delete this just because we don't need it, but I was just showing just so you know, if you ever need to, if you ever want to run different models while in the same session without having to have multiple windows of Abaqus open, you can do it this way. Right, and for what it's worth, I recommend whenever you're creating something you want to change the name of it, I recommend doing it at the beginning. It's a little bit finicky because sometimes Abaqus can only references the name you give it. And so if I were to create a job here on the cantilever beam, jobs I'll talk about a little bit later. And then, so that's created and it's referencing cantilever beam model. But then if I were to change this to cantilever beam tutorial model, changing the name, I wouldn't be able to submit this job because it would be searching for the name cantilever beam model and wouldn't be able to find it. So just be careful if you're ever changing names that you make all the appropriate changes to things that are referencing it. Right, so I'll just delete this for now. Okay, so to get started, I suppose we should just get started right away. I like working with the tree model, the model tree, as I noted, and simple because for the most part, we can just go from the top down to create the model, starting with parts and ending with creating a job. So let's just jump right in. So we're going to be creating, as a node, just a cantilever beam. I'm going to be applying in 2D, I'll add, and then I'll be adding a vertical force onto one of the nodes on the end. Simple enough just for a practice run with Abaqus. So let's go ahead and create the part. To do that, again, there are multiple ways you can do it. You can create part over here. You can create part from this button over here, or you can I'm just going to double click on parts over here. And so we're greeted with this window. And for us, we're going to be doing a 2D. So it gives you the option of different types of things. And so you have to select what is applicable to you. So we're going to be doing a 2D planar, and we're going to be using shell elements. So that's all right. And let's call this cantilever beam. There we go. The approximate size. This is not crucial. You don't have to worry too much about this approximate size. This is just, we're going to be creating a little, Abaqus is going to give us a sketch page to work on to create our part. And it's just giving us an approximate size without units of what we want to create. So I'm going to, let's just do 2. Again, if your size is larger than 2, then it's fine. It's just creating a little sketch window, as you can see. For here, so it's a 2x2 square that's creating a sketch. So let's go ahead, and this is going to be quite similar to any other CAD softwares that you might have used, like probably a little bit worse, or I can guarantee you it is a little worse or less straightforward. But let's just create a simple cantilever beam. And I'm going to make it dimensions of 1 and 0.1. You can see in the top left, right over here, we have the X values. I can either click or alternatively, so instead of just clicking here, what I'll do instead is down over here, we're prompted with what to do. Or actually I should have, let me rewind a bit. So down here is where any prompts and any actions you need to do is. So sketch the section for the planar shell. So we're going to select, I just selected a rectangle. I could use any other shape or any of the other tools. And so pick a starting corner. So I could either just click here, or I'll just enter 0, 0. So it is now set 0, 0 as my origin. And then I'm going to then do the same thing and do 1, 0.1 to set this. I could have done it the same way just by using my mouse, but if in case you have any specific measurements that just can't be found with the mouse, you can enter it here. One extra detail I'll be applying here is I'm going to make this edge or this face of the cantilever being rounded. This will just add a little bit of complexity later on with our meshing, just for a little bit more of a teaching moment. So what I'm going to do is there might be better ways to do this, but I'm just going to do it this way. Adding fillets on either side. So down here, I clicked on fillet over here, and I'm asked to select a fillet radius. So I'm going to do 0.05, and now select the first entity near the end to be filleted. So I'm going to be selecting these two, and there we have it. We have a fillet, and I'm going to do the same thing over here. Boom, boom. And so now I'm done with those, and I can click X, cancel procedure. And so now I'm done. So now normally I could just click done, but here it's a little bit over-defined, you'll see. So it's saying that it's over-defined. So I'm just going to delete this sketch entity, this dimension. There we go. Done. And now we can leave the sketcher. Excellent. So now we have a 2D cantilever beam. Let me just return to default view. Notice that I started panning and rotating. You can do that using in the top over here, look at my mouse. You could do that with the pan button or the rotate button. Alternatively, I'm using the shortcut keys, holding Control Alt and then left click to rotate, and Control Alt middle click to pan. And then also I'm scrolling just a scroll wheel without Control Alt to zoom in and out. And I believe you can also, so Control Alt and right click to zoom in and out alternatively. You can change these if you don't like these, because it is a little odd to be holding Control Alt all the time. I just got used to it before knowing you could change it. You could head over, sorry, I'll restart, from Tools down to Options, View Manipulation, and it gives you a bunch of options. So this is the basic Abaqus CAE options, but then there's also SolidWorks, which is control, and just there are different options, different configurations. It doesn't look like it allows you to customize your own, but I'm sure it's possible, but I haven't really worried to do that. But just showing you guys this, just so you guys are aware. One thing that I briefly mentioned, but I didn't go too deep on, is that when I picked when I did my sketch, I didn't specify any units. I didn't say if it was in meters or millimeters, inches, feet, what have you. In Abaqus, and this is true for all other FE packages, they don't give you, or they don't let you choose a unit like it is in SolidWorks, for example, where you can choose in the bottom right which units, MMGS or what have you. And so for that reason, you have to be consistent with all your units throughout the entire model. So when we're creating a material later on, and we're specifying a Young's modulus, we have to make sure that our units are consistent with the rest of our like dimensions over here. So if we used SI units, which is what I was doing, so I did 1 meter by 0.1 meters, we have to be consistent by using SI units later, or else our resulting stresses, for example, that we get when we want to analyze our simulation are going to be in those corresponding units. So that's just something to keep track of a little bit later on. One little side note before I move on to the next module, or the next step rather, is you're not limited to only creating parts within Abaqus. The Abaqus part sketcher is all right, but it's not great. And I think it's definitely okay for simple geometry, and it's beneficial because then you can go into here, click on features in the model tree, and you can directly edit the sketch if you need to. And then edit the sketch or any features that you've done. And so it's a little convenient to do any simple features or simple geometry in Abaqus. But certainly for more complex geometry, or maybe some geometry that you're getting from a different company or a different source, where they're just giving you a part file, you can import those too by going to File, Import, Part. And so here you can just go ahead and import, and you can number of different file types. You have SolidWorks part files, but you also have step files, IGES files, CATIA files, SAT files. Yeah, so all of them work. They all work just as well. The only difference is that you won't be able to change any features on it directly or easily. Right. Okay, so let's move on. The next thing I want to do is I want to associate a mesh to this part. I should mention that this is not something you need to do right away. Lots of people, and I think even here, you see in the modules, they have it ordered such that the mesh is near the end, actually, right before the job meaning the simulation running. And so some people like to do the mesh at the end. I personally like to get the mesh over and done with right away. And as part of the part, you can do it within the part tree, the part subcategories. And so I just like to do it right away. So let's go ahead and doing that. And so to do it, you head over to part, your cantilever beam, and you double click on mesh. All of a sudden we see that the part has become pink. That means something. So the part being pink means something, and it has to do with how easily meshable the part is. And so if we head over here to our little color palette wheel, this is not super important, but I'm just showing it. I like to use it sometimes to see what the dealio is it tells you what each color means, and it'll change for different, if we hover the part, now we have the colors mean different things, and the pink, there won't be any pink. Just white is geometry, and then other things too. But going back to mesh, pink means that it's free meshable. So that means that it's easy to mesh any, or easy to apply any mesh onto this part. Of course, this is a very simple part, and so evidently it should be quite easy for Abaqus to auto mesh it. But you might have some cases for more complex geometry with more bends and more sharp angles, where it might be quite difficult, especially for quadrilateral or hexahedral elements, to mesh it automatically within Abaqus. And Abaqus might ask you to do more things or change the element type for it to be easily meshable. And so that's why sometimes it might be orange, and that would tell you that you can't use hexahedral elements if you had a 3D model, or you might have to do a structured mesh or a sweep mesh. Those I won't go too far into, or I won't dive into today, but they're just different manners of, or different methods of creating a mesh in Abaqus. Lucky for us, our part is super simple and it's free meshable. So let's just go into that. If we head over here in mesh, in the mesh tab, this is one of the few times that I use the tabs up here. We're going to look at the mesh controls, I think it is. Yeah, sure. So mesh controls, here we can choose for 2D, we can choose what kind of elements we want to be using. We can use triangular elements, quad dominated, or quad. Quad dominated, just like they'll prioritize quadrilateral elements. I want to have strictly quadrilateral elements, so I'll select this. And then here I could also choose, if I wanted to do a structured mesh, I could, but I'll just stick with free because that's simple enough. And this algorithm looks fine to me. Again, this part's super simple. You shouldn't have to worry too much most of the time with the algorithm that's being used to apply to auto mesh the part. So we are okay with that. And then going back, we selected control, so now we'll select element type. And here we have some more options if we want to. Again, for the sake of this course, most of the time we won't really need to worry about this, but maybe in the future in your careers you might want to worry about this. You can put in some more controls that might be relevant to you, like hourglassing or element deletion, and you can also specify second order accuracy or choose to have different integration modes. Right, or like the linear quadratic order of the element, but let's just stick with what it is. It looks fine to me. Yeah, you'll notice that here with if I selected quadratic, it now becomes an 8-noded quadratic. 8-noded quadrilateral element, whereas linear would just be a 4-noded element. Right, so let's just stick with what we have. Happy with what we have, and let's jump into it. So how do we create a mesh? To start off, we need to create a seed. So let's just seed the part. What this will do is as you can see on this little icon over here in the module section, is it'll create a bunch of dots around the part. This looks fine to me. Let's just make it a little bit simpler and make it 0.05 or not 0.01 is okay. Or 0.05 rather. So I just keep switching my mind. Apply. So now oops, I should have kept that on. We have a bunch of seeds around the part. And so this is just specifying the size of the mesh. So if we actually just stick with that, and let's click on this next button, mesh part, down here, okay to mesh part, yes. And there we have it. We have a mesh for our part. Again, our 2D mesh. However, it doesn't really look that good. We have, I mean, as far as quadrilateral meshes go, for such a simple part, we could have a much better part. And so that's where some specific controls can come into play. So I'm going to remove this mesh. I'm going to select here, and whenever you have a little black arrow on one of these buttons, it means that there are more, that it's essentially a drop down. And the way to access, you just click and hold. So I click and hold, and I'm going to delete parts native mesh. So I'm going to do that, delete the parts mesh. There we go. We don't have any mesh anymore. And so what I'm going to do is I am going to partition this part. The reason why I created such an ugly mesh is because of this rounded feature. If it was just a perfect rectangle, it would have had no problem, but it's having trouble with this feature, and so it kind of distorts some of the elements and kind of makes things a little wonky. And so I'll just delete this mesh, sorry again. And I will be adding a partition. What a partition means is I'm going to be separating the part into different regions. So to tell Abaqus, I want to treat these as separate. So let's go ahead and do that. And you'll see what I mean once I actually put it. So if we stay in these little module buttons, over here is partition face sketch. This would be the button you need if you're doing 3D, but I'm sticking in 2D. So we have a bunch of different options of how to do it and how to apply. So we can partition by using 2 points, and that for our purposes, for what I want to do, might be a good idea. Or we could do directly on the sketch. I'm going to use partition face using the short path 2 points. And so now I'm being asked to select a start point, and I want to separate this rectangular region from this semicircle. And so I'm going to click right here, and I'm going to click an endpoint. There we go, create partition. So now we have this line drawn. And so now, we're done. Select start, yeah, sorry. And then so now our part is separated into 2 regions. They're still the same parts. It's still, I'm not bending the part into 2 sections, or it's no longer 2 parts. It's just, I'm just telling Abaqus that we can treat these as 2 different sections or different regions of the part. And so what if we put the same seed and create a mesh now? Now for the rectangular region, the first partition, or not partition, the first region, distinguished by the partition, we have a very nice mesh. It's just perfect. It's just a bunch of little quadrilaterals of the same size, no distortion. it looks good. But over here, it looks fine, but it's still not spectacular. I mean, for our purposes, it'd be totally fine, but I think we can still improve it. And so what I'm going to do is I'm going to add another partition. So I'm going to delete this mesh, and I'm going to add another partition. Well, maybe this is a good idea. Select the faces partition. I want to partition this side, and I'm going to cut this in half again, but along the x-axis. Create partition. There we go. So now I've cut it in half. And so let's do the same thing. We have the seed already on, and let's now mesh it. That actually does not look that great. Let's try and make this a little bit finer. Sure, fine. It looks all right. But it's nice because we have a distinction between the top and the bottom half. However, so now let's think back to what our problem is. We're going to have a cantilever beam. We're going to be fixing this side in place, fully fixed. And I am planning on applying a vertical load onto this node here. And so it's just a regular cantilever beam that you guys would have all seen. And so you guys can imagine that the stresses are going to be highest over on this side, where the body is fixed in place. And so it might make sense for us to refine the mesh such that the mesh is finer on this side, so we have good accuracy over here, but then a little bit coarser on this side, because we don't necessarily need a super fine mesh on this side, and having a coarser mesh will make it easier, or rather faster, for Abaqus to complete the model. So let's remove our mesh. And there are a number of ways to do this, of course, but I'm just going to do a simple way. Here we have the global mesh that we specified, but then I'm going to use the second option over here, seed edges. Yeah, just seed edges. And I'm going to select these two faces. I select both of them by holding Shift for what it's worth. And I'm going to hit done. And then I can, if I wanted to, I could assign a specific mesh size. So before we get into making it finer on one side, let's just show this. We can make it, let's say 0.04, or sorry, 0.04. And here you could see that we have very fine meshes on the, or very fine seeds on over here, but then coarser on this side. So let's see what that would look like. As you can see, it's now a lot coarser in the X direction. This isn't necessarily what we want. I mean, it's all right, but I want to make it a little bit finer on the left-hand side and coarser on the right-hand side. We'll keep it a little bit fine on the end just to keep the geometry since it's a curved edge. But let's make it finer on the left-hand side. And to do that, again, a number of different ways to do it, but one of the ways you could do it is applying a bias, a single bias. I'm not sure which direction I'll do, but let's just go ahead and try it. I'm going to go from 0.02, let's say, to 0.0, oh no, that's a little bit too much. 0.5, let's try that. Delete meshes, yeah. So now I'm gonna actually flip it, flip bias, select the edge. So now I also want to flip it on this side, sorry. So now the arrows, this red arrow here is pointing the other way. And so if I apply it, now we have a finer mesh on the left-hand side, and it gradually becomes coarser. So that's pretty good. I'll make it a little bit coarser just because, again, this model is really not that crazy. But so let's do maximum size of let's do 0.03. I think that's what I've had in the past. And then do 0.01. Apply. That looks pretty all right to me. And let me change this global seed size to 0.02. This looks okay to me. This isn't the perfect mesh. I'm just doing a quick run through, but so don't get too crazy about, or don't think too crazy about what exactly I'm choosing. I'm just doing a simple thing. Well, maybe I should do it a little bit finer over here. But so you see, we have a finer mesh on the left-hand side, and it slowly gets coarser and coarser as we go over. So actually, let's quickly change. I'll try and be quick here, just to make it a little bit better. Let's go back to what we had before. Sure. Maybe this will just be fine. Sure, that looks fine to me. So we have fine over here, coarse over here. We have a little bit fine because this section of the geometry is a little bit finer, or not finer, a little bit more detailed, a little more complex. But we also have a distinction between the top and bottom half of the part. So we have this, specifically this node over here that we can use. Good, so I am happy with this mesh, and we can just move forward with the model. Of course, if we want to use triangular elements, we could have done that at the beginning when we did mesh controls. And we could have selected triangular elements, but I'm not going to mess with that because it's not too complicated. I just want to keep this mesh. If I had selected triangular elements there, it would delete my mesh. So we've completed the part, we've completed the mesh. So let's just close this little menu here for part, and let's move over to the material. We want to specify material for this part. So as I know at the beginning, we could do it from a bunch of different areas, but let's just double click on materials over here. Let's give this a name. I don't actually, maybe I could, basic material. I'm not sure. It could be steel, it could be aluminum, whatever, but I didn't, I'm just gonna be putting random values in here. You could also put a description if you want, if you're having a specific material that has special properties. But everything is specified in these menus. You can go into mechanical and you can specify plasticity. Here there is more coolant plasticity, a crushable foam plasticity. There's damage criteria that you can add, Johnson Cook, viscosity or equations of state. Bunch of things you could put in. These two, typically you don't really need them just because typically you're not really working with thermal or electromagnetic, or at least in my experience. And then here, don't have to worry about these, but sometimes you should worry about density. For static models, which is the case for me, or for this model rather, don't have to worry too much about density. You just click here and now you have material behavior that's added to our list, and you can just put in the mass density. Doesn't really matter for static models. You could just leave this blank, or you could just not include it. So I'll just remove it, click the eraser. And all I really need is the elastic properties. That is just the elastic modulus and the Poisson's ratio. There are a lot of options here. If we want to, we can have an anisotropic material where we have elastic moduli different in each direction. Same with the Poisson's ratios and the shear moduli. But I'm just going to stick with the isotropic formulation, very simple. And I'll just put in 100, E9, and 0.3. Notice I put, so it accepts E for 10 to the power of the 9. Here, this is 100 gigapascals. Earlier when I was creating my part, I was doing everything in meters. So I did 1 meter by 0.1 meters was the size of my cantilever beam. And here I have to stick, or I have to remember to stick in SI units, so that is pascals, if I want to make it, if I want everything to make sense when I run the model. So I will click OK. And so now we have this basic material. Again, that I could have found the aluminum or steel, but simpler just this way, just to do 100. Great. So now we want to, the next thing we want to do is apply this material to our part, because it's not immediately going to apply to our part. If we have multiple parts, multiple materials, Abaqus won't necessarily know which part is supposed to be what material, right? So you have to manually assign it yourself. And so to do that, you have to create a section. And now it isn't as simple as just here's your part, and there's a little material assignment thing immediately, because of course you might have within a given part, you could have different regions of your part being different materials. For example, I could have this rectangular portion of my part be aluminum, and then this little bit over here be plastic or steel. So the way that they do it in Abaqus and in other softwares too, is they have these sections. And the section is not only associated to the material, but also associated to an element type, because you could also have different types of elements. You could have 1D, 2D, and 3D elements all in the same model interacting with one another. And so you want to create a section, double click on section, and I'm going to call this cantilever beam section. And I'll keep it solid, homogeneous, and automatically it populates basic material, the one that I created. If you don't have any, or if you can click here to create a new material right away, but I'm not going to do that because I already created basic material. If you have multiple materials, you choose from the drop down which one you want. And I'm going to just press OK. So now I have this section, which is solid and for this basic material. And I'm going to go back up. This is one of the few times where you have to go back up in the tree in developing your model. But this is what you have to do. You have to go back up to the part section and click on section assignments. It tells you select the regions to be assigned a section. And if I want, I can create this set. So I'm just going to drag, not holding shift or anything. I'm just dragging, and I want to collect all of it. If I wanted to, I could just collect this part because we've partitioned it, so I recognize that this is a separate region. But I'm going to do all of it, and I don't need to create a set, but it's never. I always like to create sets just because they might come in handy later on. Sorry, I'm going to create this set, and I'm going to call it beam set, full beam set. There we go. Good. And so now we have this section assignment. This looks okay to me. I'll press OK. And so now I'll leave the section assignment thing here. But now our part is essentially done. Our part has been drawn out with the sketcher. A mesh has been applied to it, and we have a section assignment to it. So now it has a material and an element type, or not necessarily an element type, but just a formulation applied to it. Good. Moving on. So we started with part. We then added a mesh to our part. We then created a material, created a section associated to that material, and we applied that section to the part. So now we have a part that has a material, geometry, and mesh. That's good. The next thing we want to do is we need to create an assembly. And now this might not make super sense because we only have the one part that we're doing. Why do we need assembly? In Abaqus, you might have simulations where you have multiple parts in a given model that are interacting with one another, or maybe multiple of the same part that are interacting with another. And so it's just Abaqus always requires you to create an assembly. And so to do this, we're going to be creating an instance of our part. There are other options here. There are other items here that you can work with, but we're just going to be focused on instances. Instances is just the part, you're just bringing the part into your assembly. So let's just click on assembly. We are now in the assembly module. And of course, we have nothing because we haven't imported anything into our module yet. We can look from our parts. We have one part to bring in. So let's click on instances. And now we have all the list of the parts that we've created in this window over here. If we had more parts, of course, it'd be more, but we only have the cantilever beam. And so I'm just going to immediately bring it in. One thing I want to note is here it says to change a dependent instance mesh, you must edit its parts mesh. What this means here, I'm just going to backtrack. Let's not get too jumbled here, but I'm just going to backtrack over here and remove this mesh. and go back to assembly. Oops. Back to assembly. Now here, when I'm bringing in this cantilever beam, it gives me the option to choose dependent or independent instance type. And so dependent is what we had. So we had the mesh directly on the part, or what we can do is rather than doing the mesh over there, we could have done the mesh on the instance. Typically it's okay to do mesh on the part. And so that's what I had. And so I'll just quickly re-add the mesh over here. But the reason why it gives you that option is that sometimes you might need to do it directly on the instance rather than on the part, because you might have two in a given model, in a given assembly, you might have two of the same parts in the same model, in the same assembly, but at different areas of the model, and so they might have different loadings onto them, or different boundary conditions and such, and so you might need a different mesh on them. I had a finer mesh on the left-hand side, and it became coarser and coarser. But if I had a second one of this mesh that was, let's say, glued to this end and went further to the right, excuse me, if it went further to the right, we might need a finer mesh near the rounded edge, for example. Now that doesn't seem, that was just like a off-the-cuff example I just gave right away, but that's just to say that you could have one given part that you bring in, import twice into your assembly, and have two different meshes onto them. But again, we just did on our part, which is fine. And for most of I believe for the assignments, you could just do it. You just do a dependent mesh or dependent instance, and it should be fine. So now we've created our instance. It is now in this little instance tree, cantilever beam 1. There are other tools that if you bring in a second one, let's just, for the sake of it, let's bring in a second one. Oops, I'm going to delete that one. I'm going to offset it. So now I have a second one. If I want to, there are a bunch of options over here that allow you to move it around or position constrain it. So for example, I can select translate instance, and I can select this instance, done, and I can have it, I'm going to draw the vector of where it's going to move. So I'm going to draw this point to this point, and there it's moved. So then you just have these options to move things around, rotate, constrain them, and such. But again, we're only using the one instance, so I'll just delete this. I'll just be including that just to show you. I believe that's done. I'm just consulting my notes over here. Right, yeah, so I think that looks pretty good. It's, again, super simple. It would be more complicated for more complex models, but for here, really simple. So we can close the assembly or minimize it. And the next step is, coincidentally, steps. And this is where more finite element theory might come into play, but and so every simulation is carried out in a series of steps. An initial step, here it's already by default created an initial step. In every single time you open Abaqus, you'll have an initial step defined here. I can rename it if I wanted to, or actually I can't rename it, my mistake. It'll always have an initial step. It's always present by default, and here you can activate basic things like boundary conditions and interactions or contact definitions between parts. And you can see here that there's a list of interactions or boundary conditions that can be defined or activated in this initial step. The step is essentially, the initial step rather, is essentially used to initialize the simulation. You're putting your initial conditions of the part. Then it's important to create a second step for our simulations where we would have to apply a load, for example. We can't apply a load in the initial step because as part of the FE solver, the finite element solver, the load needs to ramp up in a certain way. And so the solver needs some time to apply it. And if we do it in the initial step, it would be instantaneous and it wouldn't work. And so you can create another step. And of course, you can create more than one additional step. For example, you can have a scenario where you have a step that has a load applied to the part, just a concentrated load on a point, and then a second step where the load is released, for example, and displacement is applied to it instead, displacement control, and then a third step where everything is released, and then you allow for the body to return to its previous shape, assuming only elastic deformation occurred, or just return to it, or regain all elastic deformation, and then you would just have the plastic deformation if you were doing some sort of bending problem where you have spring back, for example. But so you can have multiple steps. For our case, I'm just going to create one load step. So let's create it. We're going to be applying our boundary conditions in the initial step, and then we're applying a load we're going to define our load in the load step. So that's what we'll do. We want to define it after the initial step. So this is okay. I'm going to call this load step. Again, you could just leave it as step 1, but I like to name them just so I understand what's going on in each step a little better. And here we're graded with a bunch of different options. I'm just going to keep this general. You'll keep this general, will be fine. And we have a lot of different options, viscoelastic, soils, heat transfer problems, and we also have these dynamic problems. Here, this is a static problem, but I just want to draw your attention here to implicit and explicit. If you think back to your numerical methods courses, I believe in second year, ME203 or maybe 303, actually, I'm not sure. You can think of implicit and explicit Euler methods and how the solution steps in time for each technique. These are the two techniques that are used in FEM, but are typically used for different applications. For the purpose of our course, we'll be focused on implicit FEM, as it is better suited for static analyses where you're analyzing loads on an object where it is in equilibrium, whereas an explicit analysis is typically better suited for dynamic or impulsive loading situations like a bullet penetrating a plate or just a high strain event in general. There's a grad course, ME559 Advanced FEM, that goes much more into the formulations of implicit and explicit. And so if you're interested in grad studies, you can certainly learn more about it that way. But for the sake of our course, we are just going to be fine with just doing a static general meaning. General here uses an implicit formulation of FE. So let's go ahead with that. And there are, of course, and we could change some things. We have some things that we could change. Description, I'm not going to bother with the description because I've already named it load steps, already know. But if you want, you can specify exactly that. We could call it the ramp up load. Sure. Time period. Here, we're using SI units again, so this can be expressed in seconds. Unless you're doing anything explicit or you're doing anything viscoelastic, meaning time dependent, you shouldn't have to worry too much about it, but I'm just gonna leave it at 1. But we could just keep in mind that everything is gonna happen in 1 second. But there aren't gonna be any time effects, so it's not gonna really be super relevant. And then incrementation. This is how you're going to be telling Abaqus to increment in time. For this kind of problem, we could probably just use 1 increment and it'd be totally fine. I, however, am going to decrease it just for the sake of showing you guys. And so here it's the very first step that we're going to use. It's saying 1. I'm going to make it a little smaller. I'm going to make it, let's say, 0.1. And I'm going to make the maximum size to be 0.1 as well. And so here, what it's saying is that, so we're going from time 0 to 1. Abaqus has already set that there's a maximum number of increments. So if we exceed 100 increments, then the job is going to crash and it's going to stop. Of course, you don't want too many. Like I could just set this to, I could just set this super high, and so it just doesn't crash based on exceeding number of increments. But it is a good idea to limit it, because if you're exceeding a ridiculous number, it's an idea that maybe your model is not performing as well as you want it to. And so it's good to limit it. here, the initial step, this is the very first step, is going to be 0.1, and then subsequent steps, it's going to calculate what is the optimal size. Maybe it'll need a smaller step size to do a certain to do the next step, or it can ramp up, or it can go higher. So actually, let's actually start a little smaller and keep the maximum at 0.1. But let's start at 0.05, and then the minimum is set to 10 to the -5. That is fine by me. Other, you don't have to worry too much about this, and don't have to worry about nonlinear geometry for the moment. So everything else is fine to me. We'll see this again when we run a job. So let's click OK. And so now we have an initial step where we haven't yet defined a boundary condition, but we're going to define the boundary condition. And a load step where we're going to define more things. And so specifically, we're going to define the output requests, the loads, and the boundary conditions. But let's just leave that blank for now. Next. I'm going to skip a few modules here. So I'm going to skip the output requests that I just said that I would be defining. You could totally do them in order. But I'm just going to skip a few, and these I'll briefly talk about, but we're not going to be using these in our model. I'm going to skip over to loads and boundary conditions, because that's the one thing that maybe makes most sense to help wrap up our model and really define what we're doing. So again, we've created a part, we've associated a mesh to it, we've given it a material through section assignments, and then we've put it into an assembly. We've created our step for our load. And so now let's create our load. So we can double click on load, and I'm going to call this point load. And we could say when we want to apply it. We want to apply it in the load step, and we can choose what kind of load we want to do. Sometimes you might have a pressure load where you would be distributing, this would be akin to a distributed load. I'm just going to do a concentrated force. This is just a point for it, or a point load. I'm going to select continue. And now it's asking me to select points for the load. So if I want to, I can select multiple points. I could select this point and this point if I wanted to. So let's try that. And I could create this, I create a set if I wanted to. So let's just call this the point load set 1 or set test, because I'm not going to do it this way. I'm going to just do one of the points. But if we want to, again, I held shift to select both of them. I'm going to create this set. And now we are greeted with this window, distribution uniform, fine. CF1, CF2, concentrated force 1, concentrated force 2. These are in reference to the coordinate axes. We're only in 3D, or sorry, only in 2D, and so we're not having a CF3 for the Z-axis. But so CF1 would be a force in the X direction, and CF2 would be in the Y direction. So we are only going to apply load in Y. So we could leave X blank, or CF1 blank, sorry, and CF2 we can populate. So let's do negative 100. And so this would be newtons, because I'm using SI units. We always have to be thinking about the units that we're using in our model, stay consistent. It's going to ramp. And you'll note that I specified negative, because here the Y is going up to be positive. And so if I want to act down, if I want my force to act down, I need for it to be negative. So let's press OK. So now we have two loads here, 2 loads of 100 newtons. And that's actually okay. I was originally just going to do 1 load, but it's not a big deal. I'll just leave it as 2 loads just for simplicity's sake. I could have just selected 1 point to apply the load, but no big deal. Right. One thing that you might have noticed when I was creating it, test load, is if we go back to what I was doing, I'll just do this here. I won't create a set this time. The reason why sets are important is that sets, I'm just backtracking a bit, or going a little tangent here, is sets can be referenced. For example, there was here my sets are being stored in the assembly part of the model tree. But sets can be easier, like it's not a bad idea to define them all the time, just because if you're if you keep on defining, or if I keep on naming these 2 points to define things, maybe I'll apply a second load. So let's call this horizontal load actually. And instead of clicking these 2 points again, I can click over here, over on the right-hand side, bottom right, and click on sets. And I can select these. And so it'll automatically select the 2 ones I defined earlier. And so let's go ahead and actually, why not, create a load in the X direction. So let's do, how about 20 and leave this blank. But what I was coming back to here is the amplitude. So here it's just going to ramp linearly from 0 to 1. But what I could do instead is I could define an amplitude. And so I could have just defined it earlier, but I'll define it right here by clicking right here. So I'm defining an amplitude, amp1. So I'll just do piecewise ramp. Tabular is okay. There's a bunch of different options that you can use. And now I can define in my table how I want my thing to ramp. So I can go, I'm just going to quickly go through this and you'll see what this is doing. Time 0, and then I'll do an amplitude of 0, of course. And then I'll do 0.5 time, and I'll make this 0.075, or let's see, 0.075 is okay. Press enter and it'll create a new line. And I'll do 1 and do 1. So we'll see in a second step time, that's okay. If you have multiple steps, this might be relevant. You might be concerned with the total time in the simulation or the time in the specific step if you have a second step or a third step, as I mentioned earlier, but this is okay for us. Good. And so now we're using this piecewise ramp instead. Let's press OK. So now we have a force in the Y direction acting downwards. We have a force in the X direction acting to the right. And the force in the X direction has an amplitude, a piecewise ramp. If we want to quickly look at what this ramp looks like, obviously it might be a little intuitive or simple for you guys, but if you have more complicated ramps, you guys can take a look over here. I think it's over here. Let me just here, right. So when we've created, so when we've created an amplitude, if you go to plugins, tools, amplitude plotter, this option will appear, amplitude plotter. And so I've only created one amplitude, so I can just plot this guy. And so now it's going to plot like this. It's not perfectly piecewise because I believe I made it, let me go back here. I guess it curves a bit just so it's not as sharp with the for the solver. But so that's what it's going to look like. That's how I'm going to be ramping it. And whereas with my vertical force, my ramp is just going to be linear from 0 to 1. Or 0 to 100% rather. The 1 here represents 100%. Good. So let's now add a boundary condition. We want to fix this side. So let's click on boundary condition, fixed left side, come up with a better name than I did. I'm going to initialize this or activate this in the initial step. Or actually, I'll just do a load step for now. I'm going to be putting the initial step, but I'm just going to do this for now. Don't worry about this for now. You'll see what I'm doing. I'm going to apply a mechanical boundary condition, and there's a bunch of different things you could do. I'm going to just do the symmetry, anti-symmetry, and caster option. I'm going to select a set. I don't want to select one of the options, but I'm going to define this face here, this line, and I'll create a set, why not? Left face set, sure. And here I can choose what I want to do. So again, 1 represents X, 2 represents Y, 3 represents Z. Obviously, we don't have anything in the Z direction because we have a 2D model, but you could but these are just the presets. Sorry, these are just the preset things that they give you. And so I'll just go choose Encaster. And so that just is fully fixed. You can see every single value here, all the displacements, the translations they use, and all the rotations are set to 0. So I'll just select that. And so now we have this Encaster definition over here. For the sake of it, I'm just going to show you what else you could do here. We're not going to be applying it here, but I'm just going to show you what you could have done. You could apply a displacement or velocity definitions here. And so I'm going to do it to the same, or let's do it over here to this point here. I'm not going to create a set. And here, what did I have here? I have displacement / rotation. So if I want to apply a specified displacement rather than a load, for example, I could say that I want it to move 10 meters, or 10 meters might be a little excessive. Let's do 0.01 meters in X. And then I could also have a rotation about the Z axis or what have you, you know? And I could do the same thing. I can add a specified amplitude to it. I'm not going to apply this, but this is just to show you that you can do this. And this is also another way, before we use the other option that gave us all these symmetry conditions or Encaster here, and all those were just, again, preset options. But here you could specify, I want it no movement. This point is not allowed to move in X, and is not allowed to move in Y, for example, let's say. We could specify it that way. Of course, that wouldn't really work with our simulation very well, but you can do it that way. I could have set this face to have 0, 0, 0 here rather than using Encaster. Right. And then one thing, and this might be relevant, this will be relevant in your assignments. Had I gone over here, this first one we did, I could have also done, these are how you would apply symmetry to your model. X symmetry, what have you. These are just different presets you could use, but I'll just exit out of this. If you remember, what I did is I put this boundary condition in the load step. And so you notice if I go up to loads in the model tree, there's nothing defined in the initial step, but if I go to load step, we have these two loads that I applied, the horizontal load and the point load, which I'll actually rename, or no, who cares? I have this vertical and a horizontal load, and then I have this boundary condition load, or boundary condition that's set in the load step. But it makes more sense for me to activate it in the initial step, so everything is initialized, all the initial conditions are set. And so the way that I could do that is I could right click over here and click manager, or I can do the same thing from over here, let's do boundary condition manager. And I want this to be set in the initial step. So what I can do is I do move left. And so it's created initial step and it's propagated in the load step, meaning that it's created in the initial step, but then it's still active in the load step. It's still, when I'm applying the load, it's still going to be active here. But what I could do, if I wanted to, for whatever reason, you can have another step, and I could deactivate it such that it's created here, but as soon as I start loading, I no longer have this boundary condition. Of course, here, that makes 0 sense for us, since we want to keep it fixed. But this is just something you could do, and it might be relevant for multi-step analyses or cases where you have multiple boundary conditions where you only want some applying and some not applying at certain points, right? So I'm going to just activate here and keep it in here. But that was just to show you what is possible. So let's exit out of here. And so now we can see that our initial step now has one boundary condition. It's created this boundary condition, and then it should have here boundary condition propagated over here. So that's perfect. That's exactly what we wanted to do. Good. So now what we've done, we've pretty much done everything we need to build the model, to build the conditions that we're subjecting our cantilever beam to. The last couple of things that I want to talk about is going back up. We have I mentioned these field output and history output requests. When we run our simulation, we'll want some output measures to make conclusions off of. And so we can decide what we want our field and history output requests to be. For example, you may want to track strains and stresses in a certain direction specifically, or you might want to look at plastic strains, or you might want to look at internal energies or contact stresses, that kind of stuff. So you can define everything that you want in here. The difference between a history and a field output request is that field data is information you want on the entirety of your model generally, or at least a large region. And so those can be spitting out a lot of data or generating a lot of data for you. They'd be stored at less frequent time intervals typically, seeing as so much information is being gathered. Whereas history outputs are the opposite. They gather limited information, but very frequently. And so the use for history output requests would be getting, for example, a displacements or stresses at a specific node, for example, or a small region or a couple elements, for example. And this is useful for extracting data, and plotting it then in a graph. And so that's exactly what we're going to do. We're going to be defining a field output request. So let's see, it's already defined one by default, and it gives us, it selected the default one. So it has just regular stress in all directions. It has some strain components, equivalent plastic strain, all of these. And so I'm just going, and so we have all these options that we can choose from. And I'm going to go ahead and remove contact because we don't have any contact stresses. We don't have multiple, we only have the one part. I don't, if I wanted to, I guess since it's such a simple model, it's gonna run pretty quickly, but I don't necessarily, I'm not really interested in the forces. All I'm interested in knowing is the, are the stress and the strains and maybe the displacements too. But keeping the force and the reaction forces might not be a bad idea just for a validation sake. So I'll keep these strains. I'll have regular strains, not necessarily only plastic strain. Plastic strain magnitude. I'm going to remove plastic strain because I haven't defined any plasticity in my model. Logarithmic strains is okay. Great. And then displacements, we have translations and rotations, that's all right. And stresses, that is okay as well. Forces, reaction force and moments, I'll remove, oh yeah, this is okay. So these are just the default values, and this is, so what I have here is fine for me. Up here, you can change some things. You can change the domain, so you can choose this to be just a set, one of the sets that I defined, so it'll only generate data for those sets, or some other things, but don't have to worry about these things. I'm just gonna leave it as the whole model. And then I can also define how often I want data to be tracked. And so for a field output request, you might often not need it at every increment, but it's just the default. And so sometimes to ease the computational cost, to make it run a little faster, you might reduce how much data you're generating. And so you can do every n increments. So I can do every 2 increments, I'll output my field output request, all this information. But so let's just leave it at every n increments, or every 1 increment rather. That's fine. Typically for larger models, you might have to make this smaller. This looks okay to me. And let's press OK. And then let's create our history. Right now, the default is they just have internal energies. I'm not concerned with those. I want to choose, I'm going to select, sure, that's okay. And I'll just grab all the forces. Why not? Or this doesn't seem right, but let's just, and then the second thing is I don't want to do it for the whole model because that's a little excessive, but I'm going to choose a set. And have I selected a set? So no, let's go to actually, I'm going to exit out of here, sorry. But I'm going to go define another set. So we'll go to my assembly, define another set. And I want to know history node set. So I'm going to select a node, continue. And I'm going to select this very end node. And I might also press Shift and select these nodes as well. Press done. Great. So now I have a set for that, and let's go back to our history. And I'm going to select my set, and I'm going to click on the history node set, the one I just defined. So now, like I said, history node, history field Abaqus, or history Abaqus, excuse me. I'm going to track all this just for this set, so for those 3 nodes to make it a little bit simpler on us. So I'm going to select my displacements. You'll notice that I changed a little bit just because earlier it was doing the entire body, and now I've selected 3 nodes, and so it's a little bit happier. And so I could select, I'll select all my translations. Why not? If I wanted to, I could do just my translations if I wanted to, or maybe just my translations in X, but I'll do all of them, why not? And then I'll also go ahead and select, sure, I'll just do all these stresses here. Sure, sounds good to me. And I'm happy with that. And if I wanted to, I can track this, or I guess I'm limited to once every node. But if I wanted to, I could also do these other options where evenly spaced time intervals, or every X units of time, or I could also use time points. I could specify specific time points, so at 0.2 seconds, or at 0.4 seconds, or at 0.75 seconds if I'm interested in specific time points, which I would define over here on the left in the model tree over here. But I'm just going to do every increment. So that looks good to me. And let's do that. So I could minimize each of these. And so I'm pretty much done. In fact, I am done creating my whole model. For this cantilever beam example. I am not concerned with any constraints or context or interactions, specifically the interactions and context. Obviously, you can imagine that this is for, I'd be defining things for contact between 2 different bodies. Constraints, you can do a bunch of different things. You could be tying different nodes of 2 different parts, for example, or you can setting something to a rigid body. But again, we're not going to be really worrying about this for this example, or really for the other assignments, I don't think. But it could definitely be useful for you using Abaqus or other softwares in the future. So let's get straight to the simulation. So we've created the whole model, like I said. We've created the part, we've associated a mesh, we created a material, we created a section for that material, we assigned that section with that material to our parts, and now we have a part with a geometry, a mesh, and a material. We then, we also created or defined 2 loads and 1 boundary condition. And we defined our load step. And then we also defined the output request that we want. So let's go ahead and jump all the way down to here to jobs. Jobs is in the analysis load section. And so we can create a job. This is a simulation. So let's call this cantilever beam job. Sure, why not? And we're selecting this model. Double-clicked it or clicked OK. And here, you shouldn't have to worry too much about here. If you, in the future, for very complicated jobs, you can do a restart analysis. I won't cover what that is, but that might be useful for stopping a job halfway through, analyzing it, and then starting it back up again. Or you could also do parallelization, where you can use more than the default number of processors to make it run a little faster. But the jobs that we're going to be doing in this course are going to be so simple that you really won't need to worry about this. It's going to run pretty quick, even on the campus computers in the labs. So I'm happy with all of this. The default is OK by me. I'm going to press OK. And so now I've defined this cantilever beam job. Now I haven't yet run it. It just defined it. And so if we right click on it, we have a bunch of these options here. The 3 or the 4, the 5 most important, sorry, I keep on correcting myself, are these 5 here. Write input will create an input file. So if I actually and this might be useful. It won't be useful for the course, but this I'm just pointing it out just because it might be relevant to you guys, or it might be useful to know. You're going to write an input file. So let's just go ahead and do that. And so if we were to go to our working directory, it has now created a .imp file for us. It created it just now, 554 over here. And we can open this. Do I have a, I guess I don't have Notepad++. Notepad is all right. So this is the full model right here. Here's all our nodes and our elements. And then here's in text form, this is our materials being defined, our boundary conditions being defined, step, everything is defined. And so this is what our model is working off of. This is the code. It's not really fancy code. It's not anything like, I don't know, Python or MATLAB or Java or whatever. This is the code that Abaqus runs on, and many of the other, I believe it's Fortran, many other FE packages work on. Seems a little bit archaic. It is archaic, but that's just what it works on. So if you ever need to do anything in the behind the scenes, you could do this over here, doing parametric jobs or parametrizing things. Sorry, that kind of stuff. But so everything is working in this code. And this is just a fancy UI that we're using. Here, it's for a large job, it's always a good idea. We can just click submit and this would run our job, but it's always a good idea to do the data check just to make sure that we don't have any errors, so that we don't have to run our whole job and then halfway through an error pops up and we wasted all our time. So we just do a little data check. So it says check submitted. So I'm checking, or I'm submitting it to see if I put in, there are any errors or any mistakes in my simulation or in my model. If I forgot to assign a section, or if I forgot to do something. It says down here in the message window that the check is complete. Let's go monitor. Looks like everything's fine. Otherwise it would have said something in like an error. Here it's telling me that in my warnings, good to look at, but I put in my upload request here that I wanted U3, UR1, UR2, UR3. Obviously these are not relevant, or these don't apply because we're only working in 2D space. And here also it's not happy with, it doesn't want to give me logarithmic strain, which is okay. I'm just getting regular strain. I asked that for that anyway, but so it won't give me logarithmic strain. That's all right. So that's just telling me that. No big deal. I'm not going to bother with changing this, but this is just good to keep track of. Sometimes the warnings give you an idea of if there's anything bad with your model. If there's an error, this means that your model won't run, but a warning it'll still run with warnings. So let's go ahead and submit our job for running. It'll be pretty quick. And so while it's submitted and it's going to start running in a second, it started running already, I could click on monitor. And so this is where everything will run. Here our warnings appeared again. And here, it's already completed. It did it super quick. But so you can see, I'll try to make this window a little bit larger. If you remember what I did is I started in my step. Let me see if I can open it at the same time. Let's do steps, or no, let's open my load step, incrementation. So I set my initial step to be 0.05, and my maximum to be 0.1. Of course, I could have just set it to 1. It would have done it all in just one step, and that would have been okay. But so the way that it works is that we're in step 1, our load step, and it required 12 increments to complete the job. So for the very first, and here, and each time it used 1 attempt. There were no discontinuities in the attempts, and so each time there's just 1 iteration required. And so here we have our total time and our step time. Here they're going to be equal because we don't have a second step. If we had a second step that went from here's our first step is going from 0 to 1. If we had a second step that went from 1 to 2 in time, like 1 second to 2 seconds, then over here in our total time, it would go 1.05 or 1.2, 1.4, and here it'd be 0.05, 0.2, 0.4, right? Because it's the time for that specific step. So everything looks good. If you ever have a large model that's having trouble to increment, it might have multiple attempts, or it might be reducing the step size. But otherwise, this looks pretty good. You can see over here, this is the step size that they used. They started with my initial time step of 0.05. For the second one, they used it again. And then here they thought, the computer thought this pretty good, so we could probably do a higher step size. So it tried 0.075, was able to run it. And so it went up again to 0.1, which is my maximum. And it was able to run it still. It was still able to step forward in time. And so it just stayed at 0.1 just because I set that to my maximum. And then here it had to just it just had to reduce just because we were that close to the finishing time. We're at 0.975. So it just did this to get it to 1. So that's good. So that you can just check everything that's doing in the monitor tab. Particularly useful if you have a large job that might be riddled with errors or having trouble incrementing. So let's close this too. And so we've created a model. It ran completely, or it ran successfully rather. And we're ready to analyze our results. So let's click on results over here. Here we have you notice that over here on the left-hand side, we went from the model database to the results. And we also went from the module from like part, property, all these different modules to the visualization module. And so now we have our cantilever beam that right now is in the undeformed state, but we can click over here, plot contours on deformed shape over here at left-hand side. This is the first thing you probably want to click every single time. And here we can see what happened based on our simulation. We applied vertical forces here and here, as well as horizontal forces, and so it was stretched in the x direction and pushed down by 100 newtons and 20 newtons respectively. Of course, it seems excessive, but this is just they use a scale factor to make the deformations a little more obvious. And so here we can read this that we're plotting the von Mises stress. Red values will have the red will have a higher stress value and the blue will have a lower stress value. And so here we have 1.049 times 10 to the 5. Remember, we were using all SI units. We're consistent with our units. And so here we have a value of 104.9 kilopascals of stress at these regions here. Whereas the blue is in the order of like 60 newtons. You can change, if we click over here, or sorry, not here. If we click over here, plot deformed shape, is this what I want? Oh, sorry, I'm clicking the wrong buttons. Up here, the controls, common options. As I mentioned, there was a scale factor applied to it. It was auto-computed. They typically just, if I change it to 1 to like the uniform scale factor, so that's actually the deformation that's occurring is actually accurate. Here, it looks like it didn't even deform. If we brought it up by 1,000, it deforms a little bit. The reason why we have that it auto computes just a scale factor is just for visualization reasons. And then we can also change the contour option. So this is called a contour plot for what it's worth. And we can also change the contour options. We can go over here. I selected over here the contour options. I can head over to, I could change all of these if I wanted to, but I could also, for example, I could change this to 20 options. And so we'd have more, it'd be more continuous and less granular. I'm going to keep back to 12, the default. And I'm going to go over to the color style tab, move over to spectrum, and here I could change the color scheme that we're using. For your assignments, please just use rainbow. Please don't change this, but I'm just, if ever you want to do, if ever you're making a report that you're printing in black and white, you can just do black and white, for example, apply, and here you'd have black and white options. If you're trying to do, you could also do a reverse rainbow if that's relevant, where the lower stress values are red, the higher stress values are blue. Blue to red as well. And you can also change everything. You can add different colors, but we're not going to worry too much about this, but I'm just showing you this just so you're aware of it. But we're just going to leave it at that. So we were able to plot this. If we wanted to, we can also run an animation. So if we click on this little like action, this movie set action icon, we can have it. Oh, that is super fast. Let's make it a little slower. Apply. So now we did 12 increments, and now it's just cycling through the increments. And it's showing the stress values at each time. Animation type, or I should actually do time history, my mistake. That was doing a scale factor. And so down here, you see increment going from 0 to 12, and the step time is also increasing. And so we have the stress increasing and the cantilever beam deforming over time. So that's pretty good. I'm happy with that. I'm going to stop this. Oh no, how do I stop it? There we go. I forgot how to stop it. I'm not going to read what you want. There's a way to stop the simulation, of course. Maybe if I was just supposed to double click it. There we go. As simple as that. Just click on it a second time. I'm a little stupid. Right. So I've shown you that you can plot the contour plot or put the contour plot. You can change the colors. You can change the scale factor if you wanted to. Another thing that you can do is here we're analyzing the volumetric stress, of course, in my field output request. And so this is what the field output request does. This is or it gives you. If you had changed it, it would have been different. I can go up with my cursor over here, and I could select these different things that I tracked. So if S was for stress, but I also tracked strains, and so I could also get strain values. I can go over to U, which is my displacements. And so, of course, the end of the rod is going to displace the most. And also, I could also specify U1 or U2. U1 meaning in the X direction, and U2 being in the Y direction. That the same could have been done with my stress. I could just do emissives, or I could do principal stresses. I could do Tresca. I could do the S11. I could plot all the things that everything that I put into my field output request can be found in here. Here's my concentrated force. Obviously, this makes sense. So if we do CF1, I put I have my magnitude. My concentrated forces are only going to be over here because that's where I applied them. So that makes sense. Good. So I'm just going to return back to stresses. So that's really good. And now the last thing that I want to mention is my history nodes or history output requests. And so what we did is we grabbed history data for the two nodes on the end for on the left hand side, and we had one node on the end on the right hand side. And so we can get this XY data for any of the measures that we decided to track. And so to do that, we click over here on XY, create XY data. And so ODB history output, that's fine with me. And here we're given the option of different things. So we can do spatial displacement U1 for the 4 different nodes. I'll be honest, I should have kept track of which nodes I selected, but let's just do, what does this one do? So this would be displacement in X for node 4. I'm just not sure what node 4 is here. Plot. So this must have been on the side. So it had 0 displacement because it was fixed, obviously. Let's do. Ooh. Let me just get out of here. I think I clicked on the wrong button. Let me just get out of here. And go back to results. Sorry. There's probably a cleaner way of getting back to where I was, but I didn't know where I went. But so I could go back to XY, and so history, and let's click on 6 this time, plot. And here we saw that in the Y direction, it followed this curve here. And this makes sense. This is relatively similar to the force, the horizontal force that I applied, the amplitude that I applied. So this looks pretty good. And if we do the same thing for in Y, we have that it linearly displaced from 0 to approximately 7.5, perhaps, to the 10 to the negative 6 meters, I should note. So that's pretty good. We can grab this data. If we go to the XY data manager, we'll grab this one. So it's just temporary. We could have saved if we wanted to, but we can do edit. And now there's just all this data that we can just copy paste if we wanted to into an Excel sheet. We could also change what's on the X and Y. We can change this to be, I mean, there's a bunch of options. I'll just leave it as time and displacement. So this is good. But also I could directly go to Excel by going to plugins, tools, and then Excel utilities. Now on this computer that I'm using right now, Excel is not installed, but I could go directly transfer from Abaqus to Excel directly, and it'll create an Excel sheet for you. Otherwise, of course, you can also have just done manager. So what I should have done here is I should have done save as is, and here in the manager, now we have this one here, edit, and you could just, like, if you wanted to, you could just copy paste this if you wanted to, rather than using the plugin Excel tool. Great. So that is essentially everything with this model. We ran this model from start to finish. We built it from scratch, freestyling a bit throughout it. But otherwise, everything looks good. The last thing I want to mention for you guys, and so I'm going to try and pull up a little whiteboard. How do I pull up a whiteboard? Or maybe I'll just maybe I will just, let's see what I should be able to pull up a whiteboard. No. Okay, so what I'll do instead is, do I have PowerPoint installed here? Or actually, that paint thing is paint is okay. This will be perfect. I want to talk briefly about mesh convergence, and that's something you'll see in assignment 1. Notice that when we created our mesh, we made it finer. We had, or let me actually, let's go take a screenshot of this. And so, oops, we made this mesh finer on the left-hand side than on the right-hand side. But also for this problem, we probably, speaking from intuition, we probably could have used a much coarser mesh, meaning we didn't have to make it as fine. We didn't have to have as many elements. We could have made it a lot easier on us, or at least on the simulation. But it was okay because I was just doing this for teaching sake, and also the model was going to run super quick anyway, so I was not too concerned. But one thing that is important for you guys to learn, because it's specifically relevant for much larger models, much larger one than just a simple 2D cantilever beam, is mesh convergence. And so I'll write that down here. Mesh convergence studies are pretty much standard for any finite element model before going any further and making any strong conclusions. Because oftentimes, or pretty much all the time, you might have a case where if I plot on the X direction, we have the mesh refinement, how fine the mesh is. So we'll plot number of elements, on the X. And then here we'll have some sort of measure of interest. So let's say stress at a given point. So stress, so let's just move on to see stress at node 6 or node 4, which is the one that I first tried to. So one on the left-hand side of our plate. So let's say this, let's do this in red. This is node 4. for a given mesh size, so let's just do a number of elements. Let's just pick over here. I'm not going to attribute a value for it, but like let's say a coarse mesh, we might have a stress value here. And so we'll think, oh, that looks pretty good, that looks fine. But then if we were to make it a finer mesh, so let's say finer, like make it finer for the whole part, or just maybe finer where the stresses are highest, we might find that the stress value there is going to increase or decrease. Let's say it increases here. So if we increased the mesh size if we doubled the mesh size. And so now we see that there's a big difference, that the mesh is going to make a big difference in our solution. And so that's really concerning. And that's often the case for these problems. And so we need to make sure that we have an appropriate mesh. And so what we do is we do multiple meshes. We run the same model with multiple meshes. And so what we might have something that looks like this. Boom, boom, boom. Excuse my drawing. There we go. It's not supposed to curve up, but I just did my line wrong. But so let's just say this is a straight line. Or let's do, here, I'll just do something like this. Let's say it's converged essentially. And this is what we're talking about, mesh convergence. We want, oops, my bad. I'm a little bit of a mess today. We want to use the coarsest mesh possible that gives us a good solution. And so the coarsest mesh we've tried here is this guy over here. But obviously, this is so far from the converged solution that it's not even, we're not even going to consider it. But instead, we're going to, but we want to still use a coarse mesh just so that, because theoretically, we could just do a crazily fine mesh over here, but then we're going to have so many elements that the job might take hours or days to run. I know that I've had some, in my own research, I've had some pretty, the standard job that I'm running takes like 2-3 hours to run. And if I were to make it even any larger, it could take half a day to run a single simulation. Sometimes multiple days. I know other people in different research groups have had jobs that run that take 2-3 days to run, which is a little bit crazy. But so we want the coarsest mesh so that we keep our computation time low, but we still want our solution to be pretty good. And so oftentimes researchers will define an error tolerance, epsilon, that they might not specifically say in their research study, but they'll have a tolerance that they're okay with for, let's say it might be 1% tolerance or 0.01% tolerance, let's say. And so that means, so if this is a converged solution, or let's make this in red, if this is the converged solution, they are okay with any stress values that are in this window, right? And so with this, we are okay with all these mesh sizes, but we want it to be the coarsest possible. So we'd probably use this one. And this is a mesh that we used where we found convergence to start happening. That's what we're talking about when we talk about mesh convergence. Theoretically, you can make one over here, but we've already made this mesh, so let's just use this mesh. And so that's what we're talking about with mesh convergence. We want, the point of it is to study the mesh size, so we have a good, accurate mesh, while also balancing it with the computation time. So that's something you guys are going to be doing specifically in the first assignment where you guys will be introduced to it, but you guys will also be doing it in the second and third assignment. And the last thing I want to touch on this subject is how you're going to choose what mesh size is. So let's say you have 2,000 elements here, and then 4,000, and let's imagine that this scale is not, or this axis is not to scale. This is 8,000. You want to be using a geometric series for choosing your mesh sizes, because like going from a mesh size with 2,000 elements to 2,500 and then to 3,000, you're not going to find very much difference. It's just been, statistically, it's been shown. It's the general practice to use a geometric series. So multiplying by 0.2 or multiplying by 2 or multiplying by 3, but always using a common factor when increasing or decreasing your number of elements. So I might also, if this was my first mesh, I might have also wanted to plot one over here at 1,000 nodes or 1,000 elements, excuse me, to see if maybe I already got convergence. Maybe what would have happened actually is convergence happened over here, and it was something like this, you know. So that's what you want to be doing in your assignments. You want to be using a geometric series. You could do ×3, ×2, what have you, but you want to be showing convergence happening. And so you want to use 2, 3, or 4 or more meshes until you can reasonably state that convergence has happened. You can use a 1% tolerance, or you can use a different tolerance if you'd like, that you think is appropriate or reasonable for your study for your model. Right, so I think that concludes my presentation, my tutorial here. It was rather lengthy, I recognize, but you guys, obviously I put in some little timestamps in the video where you guys can just skip to if you want to just skip to a certain section. And hopefully this helps with completing your assignment, especially for those of you that are new to Abaqus and new to FEM in general. Of course, if you guys have any questions, I'm obviously available by email or what have you. And so you guys can send me more questions if you guys are confused with any part of this video or any part of developing the model in assignment 1. So great. Thank you very much for listening, and until next time. Okay, yeah, so thank you for sticking on and listening to this video that I've made. This video was originally made last year for when we taught this course or TA'd this course for the previous year during the summer, during the spring. But I just wanted to make an additional appended video at the end of this video here. This is what you're watching right now, just to give some extra information, things that are relevant from that students might have wanted last year that you might want this year, and also some extra notes that I noticed that I think might be valuable. So first and foremost, so this is not necessarily the same model that you just saw me making in the beginning of this video. I just quickly made a roughly the same mock-up here just so I could demonstrate some things. The few things that I want to talk about are, first, being able to hide your mesh lines, change the background. Right now we have the background that's kind of like a blue or gray gradient. We can change the background, and then we can also, again, hide the mesh line. This will make you, when you're taking screenshots of your models, of your final models, the final results of your models, and putting those into your reports or into submissions for your assignments, it might be a smart idea to change those things so that things are a little more legible, or if it's important to see the meshes, then absolutely keep them. If it's not important to see the mesh, it's more important just to see the contour plot. Then oftentimes, especially when you might be refining the mesh so much so that in one spot, all you might see is just a bunch of black specks that, for example, you see right now. If I were to zoom out right now, it's hard to really make out what's going on the part. Even if I put the contour plot on, it's hard to really make out what's going on. And you can imagine that if visually the mesh was that fine, but on a larger part that you guys are going to be making in your assignments, it might be wise to remove the mesh lines. So let me do that. To do that, use in this toolbar that you have over here, you can click on the very first button, Common Options. And it's very simple. Here we have visible edges. You can just change that to one of these different options. No edges, let's apply that. You'll see that there are now no edges, no element or mesh edges. I prefer free edges that are shown just because at least it shows the outline of your part. You can see that now there's a black outline. It just makes it a little bit cleaner, I think. This would be wise for you guys to use, again, if you guys are
submitting things where you guys are not or want to take screenshots of your models that it's not imperative that you show the mesh or the mesh refinement. You can you can turn them back on with all edges or exterior edges, just like so. Um, then, as I noted, we can change the background of let's say the graphic of the GUI. We can head over to the top tabs and click on View, and down here we bring our mouse down to Graphics Options. We can look at these options, specifically viewport background. So right now it's being set as a gradient from looks like black to gray. We can change this to being solid. If we just solid black, I guess it's not quite black. It looks more blue on my screen. Not sure what it looks like for you guys. But I'm going to change this to white. That way it'll just blend into paper or blend into your Word documents or whatnot. And it might be a little bit better might be a little better for your screenshots. So that's a good idea for you guys to do for your reports, I think. Right, so we covered mesh hiding or including mesh lines. We covered the background of your FEA your Abaqus window. Um, the next things I want to talk about are just a few couple things that again we can still do in the visualization area or module, I should say. The first one is if you want to just like I mentioned that you guys can grab like history outputs and grab them at specific like we grab them at this node and then these other two nodes over here. But if it's a little bit of a hassle to specifically define those nodes in your history output and then have to go through this whole create XY data, create the plot, extract the Excel data and whatnot. If you want to just get a little quick like see if this thing passes a smell test, or if you just want to just like probe the values itself from here without having to create a whole history output, you can do you can go over to tools, query, and then you can probe the values over here. So we can these are general queries that you can like check distance of between two nodes, for example. You'll see I'll pick these two nodes, and down here at the bottom it shows me uh, the like base distance for the undeformed part. So it was 12. Now again, this is a different part. This is I just quickly made it it's not exactly the same part, and then also deformed values. Again, same thing for like if you're interested in the mesh information here, I have 598 elements, 667 nodes. They're of this type. That's not super important to you, but maybe it's important to you guys for knowing how many elements you guys have. You guys can publish that stuff. But the main thing I want to bring you guys' attention to here is the visualization mode queries. So these queries would only be available to you if you're in the visualization module, because it only makes sense to have them here. So specifically, I'm looking at probe values. So probe values will bring up this window here. And so we can select, well, we can just essentially look at every single node. I guess it's every element here instead because I'm probing elements. I am on element 525, and we can read that I clicked on it just so it would like enter and save. And I have a a MISI stress value of 2700 roughly. And as I move my cursor around, it'll just automatically update. And I can click another one over here, click another one over here, and it'll just create a little list of elements that I might deem relevant. So that's a really neat or like a cool way of easily just getting specific data at specific points because it's not super intuitive or not intuitive, but it's not the smartest idea just to try and like deduce based off the color of the contour plotter by making the contour plot a lot less granular. And so yeah, it's a better idea just using the probing method. Yeah, and so in the same way we can do this by checking the nodes. And so, of course, it's better to get the MISI's stress at the integration point of the element. But for example, I wonder, kind of like freestyling this as we speak, if I were to probe. So right now, so I have I swapped my contour plot to be distance, or no, sorry, distance displacement, the U here. If I even wanted to change it to like U1, let's say, uh, being displacement in the X, or let's change it to U2, displacement in the Y direction. I can then do for nodes, I can probe values and I can uh, take a look at what each node has. So I can click a few nodes here and it'll give me the U2 value for those specific nodes. So this is a little handy trick for quickly collecting data from different nodes and different elements that you might be interested in. Last but not least, I want to have a quick discussion. I'm going to be exiting the visualization module. You might notice that the mesh looks a little bit different than what it looked like uh, when we were building the mesh together in the video. It looks a little bit cleaner, and so that's what I want to talk about. In the video, when I was making the mesh, and I'll just remove everything here. I might even also, how do I remove partitions? I think I have to go to features and partitions. Here we go. I'll delete these over here. I was okay in the video of using just free meshing, and that's when keeping it pink. In your assignments, I would encourage you, and now it's not even encouraging, it's actually I'm telling you, please use structured meshing. The reason why we want structured meshing is it generally will make a cleaner and more consistent mesh, or let's say more symmetrical mesh across your part. If we were to just or let me let's put, let's say 1 here. How many? That seems fine to me. Mesh this part. Right now we're using free meshing. Of course, it was pink. We have, if we want to take a look back to the controls, we're currently set to quad free. You can see that without using the partitions, it looks a little bit janky. If we were to set it to controls to structured over here, delete the mesh, of course, set screen, of course, you'll notice that now, this is a little funky, and this is why we still need to have these partitions to make sure that the mesh is optimal. But you'll notice that the mesh looks a lot different. The elements might look from one element to the next a lot more consistent. Now let's quickly make these partitions again. I'll do a little differently than I did in the video. Here, I'm just I clicked on the first button rather than doing creating a partition from 2 lines. I'm going to just do it off a sketch, and I'll just do it like this. Boom, boom. There we go. Now we have our partition. Now we're back to free meshing. Let's recall we have it pink. Let's seed it and let's mesh it. And this is looks like pretty much exactly what we had in the video, where it looks fantastic over in this rectangular partition or cell. But then when we have into the semicircle or quarter circles, it doesn't look, I mean, it looks fine. It's certainly usable, especially in a tutorial or introductory situation like this. It is certainly okay to use this kind of mesh. However, in your assignments, please do not use free meshing. Please use structured meshing. You'll see that the difference is pretty apparent. Here, let me just select all this, and I'll just change this to structured meshing. You see it, each of these cells, the what do you call it? The meshing is symmetrical from one to the next, and so that just makes the solving, just makes the iterations in the computer, like in the back end, a lot easier and a lot more accurate. So it's just a really good idea to do quad structured meshing whenever you can. Of course, there are situations in the real world where you cannot. For example, you might need to use triangular elements, let's say, instead of using quadrilateral elements, because it becomes too difficult to create a good quadrilateral mesh. But for the sake of these assignments where the meshes that you'll be creating are relatively simple, you guys should be able to make structured quad meshes without a problem. especially when you're getting to assignments 2 and 3 when you'll have a little more experience under your belt. Right. And just a quick note, the reason why we're using quad instead of triangular is you'll learn this in the course, of course, from the professor. Triangular elements are great, especially great when you're tackling very difficult geometry. However, quadrilateral elements are a lot easier for the computer to calculate the stresses and the displacements for every single iteration that it's going through. And so if you can use quadrilateral elements, or if you're in 3D hexahedral, then that is a preferred way of doing it. It's only favorable to use triangular or tetrahedral elements if you cannot do it, or if you don't if you cannot do it and you're just trying to be quick. So that's the main idea that I want to get across. So again, use structured quad meshing for all your assignments. I don't want to see any triangular meshes or quad dominated. I would like to see again structured quad meshing. That is all that I believe I have for you guys in this little appended extra little video. Thanks for staying on again. If you have any questions, email me, message me. I'll be happy to answer them. Thank you very much.